Chapter 9, Module 2. In this module, we shall discuss how a continuous function f from a topological space X to another topological space Y gives rise to homomorphisms between the corresponding homology groups. Before that, we compute the homology group of any n disk Dn. Let us start with this example. For a closed n disk Dn, when n is greater than or equal to 2, we shall show that Hk Dn is trivial for k greater than 0, and H0 Dn is z because Dn is path connected. Now, let us take a point x from Dn. If f is from delta k to Dn any k simplex, then we wish to define a k plus 1 simplex Cxf from delta k plus 1 to Dn as follows. For any s belonging to dk delta k plus 1, we define Cxf s is equal to Fs. That is, Cxf is defined in such a way that it makes the following diagram commutative. To define Cxf on any point z belonging to delta k plus 1, we must observe that all the vertices of delta k except the one having 1 in the last component are in the image set dk delta k plus 1. Secondly, any point z belonging to delta k plus 1 lies on the line joining 0 to 1 and x0 x1 up to xk comma 0, which is a point of dk delta k plus 1. That is, the point z can be expressed as a linear combination of the points 0 0 etc. up to 1 and the point x0 x1 xk comma 0. Thirdly, Dn is a convex set. With these observations, we define for every t belonging to the closed interval 0 1 a function Cxf z equal to Tx plus 1 minus t of f x0 x1 xk. Since f is continuous, Cxf from delta k plus 1 to Dn is also continuous, because Cxf as defined earlier is just a linear combination of continuous functions. So, we get an assignment f goes to Cxf, which defines a map from Ck Dn to Ck plus 1 Dn by extending this assignment additively over Ck Dn. And it can easily seen that this function is a homomorphism. Also, it is not hard to prove that delta k plus 1 Cxf is Cx delta kf plus minus 1 to the power of k plus 1 f. Therefore, if we take a point f from zk Dn, then delta kf has a value 0, which implies that delta k plus 1 of Cxf is equal to minus 1 to the power of k plus 1 of f. That is, the point f which we have taken from zk Dn is now a member of BKDN. Hence, HKDN is ZKDN by BKDN, the quotient group is a trivial one for every k greater than equal to 1. Now, one thing we can note here that in the above example, we only exploited the fact that Dn is a convex set. So, therefore, we have even more general example that if we start with a convex set X, then HKX is trivial for every k greater than 0, and again convex set being path connected, H0x will be Z. As pointed out in the introduction, we wish to define some functions, some homomorphisms between homology groups to be induced from continuous functions between topological spaces. For that purpose, we wish to define, rather construct certain functions between the chain complexes Cnx and Cny when a function f is given between two topological spaces x and y. Given any continuous function f from x to y and any s belonging to Snx, we consider the composite f composed s, which is once again a continuous function. Therefore, f composed s is a member of Sny, and so each continuous function f induces a map from Snx to Sny given by S maps to f composed s. Now, since Cnx and Cny are free abelian groups on Snx and Sny respectively, we get a homomorphism Cnf from Cnx to Cny described on the generators by Cnf operated on S is equal to f composed s for every s belonging to Snx, and then we extend it linearly on the whole of Cnx. Now, we prove a theorem which says that if x and y are topological spaces and we are given a continuous function f from x to y, then that f will induce a homomorphism Cnf from Cnx to Cny, which is given by Cnf operated on any element summation Sj of Cnx and give a member summation f composed Sj in Cny. Now, suppose x and y are two topological spaces and f is a continuous function from x to y. Suppose two chain complexes are given, one is Cnx delta n and the other one is Cny del n. Then we can prove that the following diagram commutes. We have already defined the boundary homomorphisms delta n from Cnx to Cn minus 1 as well as the boundary homomorphisms from Cny to Cn minus 1 y. We have already got the expressions for the induced maps Cnf and Cn minus 1f. One is from Cnx to the group Cny and the other one is from Cn minus 1x to Cn minus 1 y. Then this diagram commutes means Cn minus 1 f compose delta n is equal to del n compose Cn f. Let us try to prove this theorem. Since Snx generates the free abelian group Cnx and Cnf, delta n and del n are homomorphisms, it is enough to prove the result on the set of generators. So, we start with taking a point from Snx, that means a generator of Cnx, and we will show that Cn minus 1 f compose delta n operated on S will give the same result as del n compose Cnf operated on S. Now, del n compose Cnf operated on S is del n operated on Cnf S, but that is equal to del n on f composed S by the definition of Cnf, but that is again equal to summation minus 1 to the power of I f composed S composed di I equal to 0 to n. But that is the same thing as Cn minus 1 f operated on the element summation minus 1 to the power of I S composed di I equal to 0 to n. Whatever written inside the brackets is actually delta n S. So, what we get is del n compose Cnf operated on S is equal to Cn minus 1 f compose delta n operated on S. From this theorem, we get a corollary that for each n, Cnf will take the whole of Znx inside Zny. That means, cycles are mapped to the cycles. Also, Cnf will map the whole of Bnx within Bny. That means, the n boundaries are mapped to the n boundaries. If n is less than equal to 0, the results are trivially true. Now, let us assume that n is greater than 0. If we wish to prove the first one, then we start with a point z from Znx, and since it is in Znx, delta n z will be 0. So, the theorem says the commutativity of the diagram gives that del n Cnf z is equal to del n compose Cnf operating on z, and that is equal to Cn minus 1 f compose delta n operated on z, and that is equal to 0. For proving the second part, we start with a point B from Bnx. Since it is a point in Bnx, there exists some C in Cn plus 1 x such that delta n plus 1 C is equal to B. And so, Cnf B is equal to Cnf compose delta n plus 1 operating on C, and that is del n plus 1 compose Cn plus 1 f operating on C, and that is equal to del n plus 1 Cn plus 1 f C. So, we have the result, and this corollary helps us to define a homomorphism between Hnx and Hny corresponding to a continuous function f from x to y. And the map is very naturally defined, that if we start with a continuous function f from x to y, then we can very well define a function h n f from h n x to h n y for every n greater than equal to 0 by the formula that it takes an element of h n x. A typical element of h n x will look like z plus b n x, a coset of this form, where z is taken from z n x. We define the map as that it takes the point z plus b n x to the point C n f operated on z plus b n y. As we have already proved in the corollary that C n f takes all the cycles to cycles, z will be mapped to a cycle of y via the map C n f, and therefore, C n f z is a point in z and y. So, the right side expression is inside h and y. Now, the function is well defined, follows from the second part of the corollary, because if we take two representatives, one is z1 plus bnx and the other one is z2 plus bnx, they represent the same element. So, that gives z1 minus z2 is a boundary in x. So, CNF will carry z1 minus z2 inside b and y. Now, CNF z1 plus b and y is then equal to CNF z2 plus b and y. This proves that the function is well defined. It is now to show that h and f is a homomorphism for every n greater than equal to 0. Now, h and f operating on sum of two elements of h and x, that is z1 plus bnx plus z bnx, will be equal to h and f operating on z1 plus z2 plus bnx by the definition of addition in quotient group, but that is equal to CNF z1 plus z2 plus b and y by the definition of h and f. Once again, we know that CNF is a homomorphism. So, CNF z1 plus z2 will be splitted into CNF z1 plus CNF z2, thereby giving CNF z1 plus b and y plus CNF z2 plus b and y, which is equal to h and f of z1 plus bnx plus h and f of z2 plus bnx. So, this proves that h and f is a homomorphism for every n greater than equal to 0. So far, we have constructed successfully the homomorphisms h and f from h and x to h and y corresponding to the continuous function f from x to y. As in case of simplicial homology, we may expect that these h and f must have the functorial properties, so that singular homology groups actually serves as covariant functor from the category of topological spaces and continuous functions to the category of abelian groups and homomorphisms. The following theorem shows that the induced homomorphisms satisfy functorial properties. For each n greater than equal to 0, we want to show that if I is the identity map from x to x, then h and I from h and x to h and x will represent the identity homomorphism. And the number 2 is that if f is a continuous function from x to y and g is a continuous function from y to z, then h n g composed f is equal to h n g composed h n f. Let us prove this theorem. We start with number 1. The definition of HNI says that HNI operating on z plus Pnx is equal to Cni z plus Pnx, where Cni s is equal to I composed s for every s belonging to Snx. But I composed s t is equal to St for all t belonging to delta n, and so I composed s is equal to s for every s belonging to Snx. Since Snx generates the set Cnx, Cni on any member phi of Cnx is equal to phi, that is Hni z plus Bnx is equal to z plus Bnx, which shows that Hni is the identity homomorphism. For the second one, we start with two continuous functions f and g. One is from x to y and the other one is from y to z. For each n greater than equal to 0, so h n g composed f operating on z plus Bnx will be equal to Cn of g composed f z plus Bnz. This follows from the definition of h n g composed f, and that is equal to g composed f composed z plus Bnz, because we know that Cn of g composed f z is defined as g composed f composed z. So, that is equal to, since composition of maps is associative, it is equal to g composed f composed z plus Bnz. But the definition of Cng says that Cng of f composed z is equal to g composed f composed z, and thereby give Cng of Cnf z plus Bnz. But that is equal to Hng of Cnf z plus Bny, so that it is equal to Hng Hnf on z plus Bnx. That means Hn g composed f on z plus Bnx is equal to Hng composed Hnf operating on z plus Bnx, so that Hn g composed f is equal to Hn g composed Hnf. So, from these two functorial properties, we can state this theorem that singular homology defines a covariant functor. We denote the functor by H sharp, which takes the objects of top to the objects of the abelian groups and homomorphisms, the category. So, if I take x tau, a member of top, that will be assigned to Hnx for each n, and for y sigma belonging to top, we assign that to Hny, a member of AB. For the morphism f from x tau to y sigma, the functor assigns that morphism to the morphism Hnf between Hnx and Hny. since the functorial properties hold, we can easily see that it is defining a covariant functor. In the next module, we shall see that these functorial properties can be used to draw several powerful conclusions. With this note, we end chapter 9, module 2.